Before we take a look at how TCP is going to handle that lost segment, just want to give you a quick note here on this cumulative acknowledgement scheme. Here's the visual for it where the server is sending that acknowledgement back and also indicating the next sequence number it expects to see. And that is why you'll also see this called forward acknowledgement. So cumulative acknowledgement, forward acknowledgement, really the same thing. That's the entire principle where the recipient is sending the ACK back and saying, okay, here's the next sequence number I expect to see. And that's where error recovery does come in. Because here you can see, of course, we've lost sequence 6000, and that's what happened at the end of the last video. So 2000, 4000, 8000 get through, the server's looking at it and saying, okay, the next number I really expect to see is 6000 because I see the pattern. This one didn't get here, I haven't seen it yet, so I'm going to send an ACK back. And that is where the error recovery comes in. And the error recovery is really being performed by the sender because when host A gets that ACK back from server A, and it says acknowledgement 6000, the host is going to say, wait a second, I sent that one and then I sent another one after that. So it's going to say, okay, I realize what's going on. Let's retransmit. It expects to see 6000 next. So that's what I'm going to do. So once that one is sent, then the server gets that one. It gets 6000 now. It already has the next one in line, 8000. So then just that quickly, we're back on track with server A saying, okay, I'm acknowledging 10,000, which is the next sequence number I expect to see. So a couple of questions probably come to mind just when you're looking at that, because like I say, in life and networking, one answer can lead to two more questions. And that's certainly true of this process, because the first question I had when I saw this was, well, how does the sender know how many segments to send before it has to get an acknowledgement? Is there a number, and how do I set that number? And also, wouldn't it be easier and faster to detect problems if the recipient sent an ACK for every segment? Wouldn't that make more sense? One in acknowledgement, one in acknowledgement. Wouldn't that be faster? Well, we're going to answer those questions while we look at these two new next TCP features. They're not new, but they're definitely next. Flow control and windowing. And going back to the three-way handshake, one of the values that's negotiated there is the size of the window. And this is the number of bytes the sender can transmit without receiving an ACK. There's a limit. And when that limit is reached, it's like, okay, I got to hear an acknowledgement or I can't send anything else. And again, that's the little conversation. The host might say, 7,000 bytes at a time. And the server might respond with, let's start with 4,000 bytes and go from there. Now, the important thing to remember about this window is it is dynamic. It is not static. So when they come to this agreement, say at 4,000 bytes, that doesn't mean the size of the window is going to stay at 4,000 bytes. So that's why you will see this called a dynamic window. You'll see it called a sliding window because the window value itself can change. Because what happens is, as the recipient in this case is receiving the data and saying, you know what, I'm not seeing any errors creep in, I'm not dropping any segments, we should go a little faster. So one of the ACKs will have an indication, pardon me, that says, hey, here's your ACK, and by the way, let's enlarge the size of the window to 5,000 bytes. And then later, as the server sees little errors start to creep in, maybe some segments get lost, then it says, hey, here's your ACK, and, let's slow it down a little bit. So it's interesting to note that it's the recipient of the data that's actually controlling the flow. You would think it would be the sender, and the sender just keeps going and going a little faster. It doesn't work that way. It's actually the recipient that's continually saying, hey, let's pick it up a little bit, let's hit the gas. Hey, wait a minute, let's slow down a little bit. Now, what I'm showing you right now is that UDP header that I mentioned. Because, we've seen all the advantages of TCP. We've seen the error recovery. We just saw flow control, we just saw windowing, and you can see actually some of the fields that we've referred to. There's the source port and destination port. More about those port numbers very soon. But with the sequence number, the acknowledgement number, you see the fields there, and you see the window, and then there's finally the data after all of this other stuff. So that's our TCP header, and we'll put that next to the UDP header, which I made larger, but you can also see that it has much fewer fields, many less fields than TCP does. And you'll also notice that it can't do windowing because there is no window field. It can't do sequence numbering, it can't do error recovery, it can't do acknowledgments because there's no place to put an acknowledgment number and a sequence number. And that's kind of why we can take a look at the headers and just say, okay, why do we even use UDP? What is the advantage here? And the advantage is that TCP's overall overhead, and that one word describes it all, UDP's advantage over TCP is overhead. UDP's header is much smaller. There's much less overhead involved in working with that. And also, beyond the cost of the headers, because I want to mention this, especially if this is your first networking course, that everything we do on a Cisco device or any vendor's device, doesn't matter. Everything we do on a laptop, everything we do on a tablet, everything we do, especially on a switch or a router, it comes with a cost. A little hit to the CPU, a little extra work here, a little extra work there. And, the TCP overhead doesn't seem to be that big a deal when you're just looking at, one segment. But we're not looking at one segment. We're looking at a lot of segments. So that's a header that not only, it gets attached to every segment, that's a little extra work. It takes up a little extra bandwidth because the header's bigger. And then, of course, the device on the other side of that connection has to unpack that header, if you will, so it's a little slower. And also, the three-way handshake itself and the forward acknowledgement scheme itself, those are generally seen as positives, but they do use bandwidth. TCP is using bandwidth to make that three-way handshake happen. The forward acknowledgement scheme, the acknowledgement scheme period, uses a little extra bandwidth. There's a little more work for the devices involved. So it's using bandwidth that UDP does not as well. So that's why you tend to see, or do see, UDP with so many important network features, including DHCP, is it has much less overhead than TCP does. And that's something to remember as we go forward into our routing studies as well, because it's not something, when you see all these features that you see on the switch or on the router, you don't just go to work the next day and, turn them all on. You turn on the ones or bring in the ones that are going to do you some good. But remember, everything we ask the switch to do, everything we ask the router to do, there's a little bit of a cost, and that cost does accumulate. Now we're going to leave the TCP-UDP differences behind for a moment and remind ourselves of two similarities, really. They both run at the transport layer. We've got that down. And coming up next, we're going to look at this mysterious term called multiplexing. Sounds complicated. It's really not, but it's also going to introduce you to those port numbers we saw in both the TCP and UDP headers, and that is coming up next.